Hello, welcome to the last day of lectures. Um, we do have class Friday where I'm going to do example problems from chapter 12, but this is the last actual PowerPoint lecture of the semester. Um, yeah, here things end. Yeah, it's kind of a neat fact. So I'm going to jump right into it. What we've been talking about this chapter so far is heat and the transfer of heat. How that if you change the temperature of something, you need to either add heat or take away heat if you're decreasing temperature, or to change the phase. And I was all like, Q equals MC delta T, Q equals ML. This is all about heat. Blah, 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 blah. But what I haven't talked about is how we transfer heat, how we go, you know, how does heat actually move? It's all well and good to say if you add heat to something, you increase the temperature, but how do you add heat to something? I mean, it's the velocity of particles. If I want to make something move faster, I go and like push them. And it can't be as simple as just pushing each individual molecule. So what the fuck? So to change the amount of heat in something, there are three ways to do it, known as the mechanisms of heat transfer. The three mechanisms for heat transfer are conduction, convection, and radiation. And basically, what I'm going to do today, all day, is I am going to explain these three things: conduction, convection, radiation. Here's the idea. Let's start at the top. Conduction. Conduction is the simplest method of heat transfer. Conduction is anytime you take a hot thing, or anytime you take something that's two different temperatures and put them together, they're going to reach thermal equilibrium. That's what we were talking about all the first half of this chapter. Conduction is heat transfer by two things at different temperatures touching. What happens is, as we know from last chapter, in cold things, the molecules kind of move slowly. In hot things, the molecules are really going around really quickly and just go around. Well, if you got something that's kind of moving slowly, and you got something else where all the molecules are going real fast, and you put them next to each other, what's going to happen is these fast-moving molecules are going to keep hitting the slow-moving molecules till everyone's going at the same speed. That if you have, go mosh pit concert style, that if you have a bunch of people running back and forth and back and forth and back and forth, and someone just kind of lazily walking through the middle, people are going to keep running into them, making them move. That's what conduction is. When you have a hot thing and a cold thing, and they touch, the hot things molecules will just keep hitting the cold molecules, giving them momentum. And conservation momentum kind of does work here, that the hot things will slow down. Really, I should say conservation energy. It's really energy. This is the whole heat thing that we've been talking about Monday. Is that the hot things will lose some energy because as they bash into the things not really moving, they'll slow down. And the slow things, as they get bashed into by the things that are moving, they'll speed up. That is the heat transfer by conduction. It is simply anytime you have two things of two different temperatures and they touch, you will have a heat transfer till they hit thermal equilibrium. This is how an electric stove works. You got a heated coil, you put a pan on it, the heated coil has fast-moving molecules, the pan has slow-moving molecules, and you just keep hitting them till they move quickly. A lot of hand-waving today, literally. And that's what it is. You jump into a pool and the water feels cold, you're losing heat by conduction. I grab this thing and it feels a little cold, I'm losing heat by conduction. Anytime you touch a thing, it is losing heat by conduction. Now, the rate at which you lose heat to conduction depends on a whole bunch of things. And I will derive the equation for heat loss by conduction in the most, I was going to say hand wavy, but that gets into this. The simplest way ever. We're just going to use logic. Let's say we have a hot thing and we have a cold thing, and we have them attached by a pipe. So we got hot, we got cold, we got a pipe. This pipe has a cross-sectional area A and a length L. Let's just use logic. Logically, the heat would transfer better the shorter the pipe is, right? The shorter the area between them, the better heat would transfer. So logically, heat will go as an inverse of length. Logically, the bigger the surface area, the better heat would transfer. And logically, the bigger the variance in temperature, the more heat would transfer. And still, only using logic, the longer you leave these things sitting together, the more heat would transfer. If I shove all of that into one equation, I get this. This equation is the heat loss or gained, the heat transfer by conduction. And what it says is the heat transfer by conduction is kappa A over L T hot minus T cold times time. Now in this equation, the first thing, kappa, that is not a K, it's a Greek letter kappa. Kappa is the thermal conductivity. It is simply a thing to say how well the object conducts heat. Interesting thing, my body is touching the air. What that means is I'm actually losing some heat by conduction because my body is about 97 degrees Fahrenheit. I'm going Fahrenheit for a second. The air is about 65-ish degrees Fahrenheit. I don't really feel heat loss because I'm used to it. I grab onto this. This feels cold to the touch. It's the same temperature as the air, but it feels cold to the touch. Why does it feel cold? Different value of kappa. It has a low value of kappa, so I lose heat quicker to it. Things with high value, sorry, it has a high value of kappa, I misspoke. It has a high value of kappa, so I lose heat to it quicker. Say that backwards. Things with high values of kappa, like metals, conduct heat well. Things with low values don't conduct heat that well. The rest of that equation, A is the area of contact. If I go from me holding this thing, the area would be the area of my hand. It's the area of contact. L is the thickness. It's how thick the heat needs to transfer. Now, you would think I would use a T for thickness, but capital T is temperature, and lowercase t is time, and both of them are in this equation already. And I don't have a third way to write a T. So we use L for thickness. And also this equation, we normally have like T and T naught, but here I have a TH and TC. Heat in conduction always transfers from hot to cold. It is always going to be TH minus T, where T is the hotter temperature, and T sub C is the colder temperature. So I don't think I said T sub H is the hotter temperature. T of C is the colder temperature. It'll always be the hot temperature minus the cold temperature. And so we can always say the heat loss by conduction through a thing is just the hot temperature minus the cold temperature. And lowercase t is the time that takes place. And so if you don't want to have heat travel by conduction, or you do want to have heat travel by conduction, you can try to edit these various things. Let me give you an example of trying to keep it from happening. Pretend this is a pipe. It's not. Let's pretend it's a copper pipe. If you go down into like a basement of a house, you might see the copper pipes in the ceiling for like the hot water pipes. What happens if this was a hot water pipe? Hot water would pass through it. In a perfect world, the hot water from the hot water heater to the sink wouldn't lose any energy in the meanwhile. Because if it goes from the sink to the hot water to the sink, any energy it loses is just wasted. But if I have a copper pipe, what's happening is this copper pipe is touching the air. Because it's touching the air, it's going to lose heat. That's why we have pipe insulation. If I wrap this pipe in pipe insulation, what I'm doing is I'm changing how much heat I'll lose by conduction. See, this insulation is made to be something with a very low value of kappa. By putting this in, I will reduce how much heat is lost to the air because I added this thing with a low value of kappa. Now, let's think about the terms. Kappa will be the constant for this insulation. A will be the area that is touching the pipe. Now, you'd like to think, it's a radius, we can do that area. But the area is the area touching the pipe. See, if I was to unroll this, and you know what? I'm going to switch to my dot cam for this because it will be easier for me to do pushing it on the ground than on the table. Come on, camera, turn on. Camera. Okay, I might not be using the dot cam for this. Yeah, there's two of me. Perfect. Nope, don't do that. Huh. Okay, there you go. Let's take a look at this. So I got this pushed in, right? A in this equation is the area that is touching. If I'm talking about this insulation around this pipe, the area that's touching is actually going to be as if I laid this out flat. That the area of the thing will actually be its circumference times its length. Because that right there, that's the area that was touching the pipe. And the thickness or L will literally be this thickness because that's what the heat's traveling through. That area is the piece that's touching. That's the piece that's touching when I unwrap this. Straight into the garbage can. That was the area that was touching when I unwrap this. And thickness is the actual thickness. And so this can reduce heat loss by its touching. Then I just ripped it. No longer a useful piece of pipe insulation. By saying this area and this thickness with this value of kappa with T hot, T cold, and time. Does that make sense? Any questions though? Now I have just like a pool noodle I can hit things with. All right, here's some values of kappa, just so you have them. As you can see, metals have high values, non-metals have low. It's of note things that we view for like, you got a winter jacket, it's full of like a down winter jacket, has a very low value of kappa. Ale has a very low value of kappa. Water has a pretty low value, but a hell of a lot higher than ale. That will come up in a second. But there's some values. I think that's a typo on diamond. In fact, I know that's a typo on diamond. I don't know the number off the top of my head, but that number is not possible. I'm going to say this is probably this. This should be 2.4, but I would double check that. That might be 2,450. It might be 2.45. I'm pretty sure it's 2.45, but I would check that at the end of class. A kind of interesting thing on this, right? Let's say you put your hand in water. I said I was going to check at the end, but I'm checking it now. Conductivity diamond. Let's say you put your hand in some water. If you put your hand in some water, shit, it is 2,000. Okay, that was not a typo. Diamonds are really good thermal conductors. Okay, let's say you put your hand in some cold water. The cold water tap in your sink feels really cold. It's actually not any different temperature than the air, though. If you have water coming out of the sink, it feels colder than the air, but it's actually at room temperature. Water coming out of the sink will feel colder because water has a higher value of kappa. Your body is used to replacing heat loss to air at room temperature and compensates. And so if you jump in water at room temperature, you jump in like 70-degree water. Like 70-degree air feels good. 70-degree water, cold as fucking hell. And it's because it has a different value of kappa that it will pull the heat out of you faster. Okay. Now, honestly, this equation, seldom used. Most people don't care about what is the total heat loss through something. They care about the heat loss over a time period. What we normally talk about with heat, at least with conduction, is the power of the heat loss or the power in the heat gain. Now, in chapter 5, we said power is change in energy over time. But we know from this chapter, heat is change in thermal energy. And if heat is change in thermal energy, that means power is heat over time, or at least the power due to thermal energy is heat over time. And since we just said Q is kappa A over L T hot minus T cold times time, that means the power by conduction is just take that equation, divide by time. And therefore the power of the heat loss or gain is kappa A over L T hot minus T cold. Now, most of the time, this comes up with people trying to prevent heat loss. Once again, this pipe insulation, that was the logic. Air is also a good insulator. That's why you'll find windows are usually double pane. Glass is an okay insulator. Air is great. So what you do is you double pane a glass and fill it, double pane the glass and fill it with a gas. That's something with a low value of kappa. It'll reduce heat loss through the window. A perfect value of kappa would be a vacuum, but nature abhors a vacuum. If you bake in a vacuum, eventually air will seep in. You fill it with another gas, it can last longer. This is why down coats work, or big puffy coat, why they keep you warm. Big puffy coats don't heat you up, they just keep your heat from leaving your body. And it's because it has a lot of air in it, a low value of kappa keeping it in. A good thermos, this is one actually, have a vacuum layer. This is actually a two-layer thing. There's an inner piece and an outer piece, and it's kind of hard for you to see, so just trust me on it, with a vacuum in between. Because of a vacuum in between, no heat can be lost. That's also why in building, you often put in various types of insulation. Insulation is just areas with low values of kappa. Having low values of kappa will reduce the heat loss by conduction. Questions? Let's do an example problem. Put myself right there. Find the energy transferred in 1 hour by conduction through a concrete wall. It's solid concrete. 2 meters high, 3.65 meters long, and 0.2 meters thick. And we're going to say inside the house is 20 Celsius, outside is 5 degrees Celsius. If I want to know the heat loss in 1 hour, there's my equation. I would need to know kappa of concrete, but I can go look it up. And I go say 1 hour. 1 hour is 3,600 seconds. Therefore, the heat loss will be kappa times the area. Now, the area is going to be this area right here. That's the area of the wall. So it's going to be 3.65 times 2 meters. I'm going to divide that by the thickness, but the thickness is this length right there. And then T hot minus T cold times 3,600. That's how much heat you lose in an hour. Which is a lot of heat, which is why we don't make solid concrete walls. Instead, concrete bricks have holes in them. Partially so they weigh less because, it would be heavy otherwise. But other part is insulation reasons. Air is a better insulator than concrete. Any questions? Okay, so this is mostly I talked about how to prevent heat loss by conduction. Let's go the opposite way. Let's try to heat things up. And we'll use something else by conduction. The oldest known way to heat things up, make a fire, right? Let's say I want to get warm. So I make a fire and I put my hands over the fire. If I put my hands over the fire, I will get hot. If I put anything over a fire, it gets hot. I'm not touching the fire. I don't have to put my hand and grab the burning logs to heat my hand. I can just put my hand above it and be quite content. This is the idea of convection. Convection is energy transferred by the movement of a substance, normally air. You see, if you put your hands above a fire, your hand gets hot because you're blowing hot air over it. Like the most epitome of convection, the most obvious thing is a hair dryer. A hair dryer is convection at its best. What convection is you take usually air, get it hot, and you just blow hot air on something. It is theoretically the air is touching. You could treat it as conduction, but it's the passing of the hot air that adds the heat change. The reason your hands get hot above a fire is if you make a fire, what happens is the air molecules actually touching the fire will heat up. As the air molecules heat up, their volume will increase. PV equals NKT. When their volume increases, their density goes down. And if we remember, density is all about buoyancy. If the air becomes less dense, whoop, it rises. And so your hands right above a fire will feel hot because you have hot air blowing past it. That's what convection is. A convection oven, if you have one, has a fan in it. That's what it is. And it just makes the hot air blow through. A regular oven is you just surround it. A regular oven, you just surround something with hot air, and it just sits there in it. That's conduction. But if you're blowing hot air over something, that's convection. A gas stove is convection because you're heating up the air and the air is rising past the pan. In general, conduction is heat transfer by two things sitting there touching. Convection is heat transfer by blowing hot air over something. Now, convection is easier to stop heat loss by convection, right? Heat loss by conduction just kind of happens. Heat loss by convection, you don't want to happen. Don't blow air, make it stationary. This is also how first, central air works, like, as in, like, first air, like heating. You're just blowing hot air. That's how it works. That's why hot air balloons work. Any questions there? I'm not going to give the equations for convection. They're complicated. Okay, so I make a fire. I put my hands above my fire. The fire gets hot. Cool. I make a fire. I stand next to a fire. You still get hot. But that doesn't make much sense because the hot air rises. And yes, the air above a fire is hotter than the air next to a fire, but the air next to a fire is still hot. That's because, my finger was stuck. That's because there's one more type of heat transfer, and that is radiation. You see, conduction involves things touching. Convection involves things blowing past but still touching. Radiation is the last type of heat transfer and needs no physical contact. Now, really, if you want to get into radiation, we're going to get into this a lot more in physics too, but here's the general idea. All things always emit electromagnetic radiation. Electromagnetic radiation, which we normally call light, is emitted from everything. Right now, you are all glowing. The thing is, the wavelength things glow at is different. Anything at room temperature, up to even a body temperature, emits in the in the infrared range. You don't see it because it's infrared. But when things get hotter and hotter and hotter, its wavelengths shift. Make something hot enough, it'll glow red. Make it hotter, it might glow blue. That's because it's just radiating heat. Anytime anything is at any temperature, all things, it is radiating light. This stack of sticky notes, it exists. Therefore, it is at a temperature. Unless it's at absolute zero. If something's at absolute zero, this breaks down. We're not going to talk about absolute zero. But this is not at absolute zero. That means right now, this is radiating electromagnetic radiation. Everything is. And in fact, the electromagnetic radiation that goes is based off the reason why electromagnetic radiation is electric fields doing this, while magnetic fields do that. That's what light is. Once again, this is a physics 2 concept. As we talked about last chapter, as long as anything is at temperature, its molecules are vibrating. If you have a molecule vibrating, it involves a charged particle bouncing back and forth. If you have a charged particle bouncing back and forth, it causes a changing electric field, radiation. So anything that is not at 0 Kelvin radiates light. This is how the sun heats the earth. The sun is hot. Citation needed. The sun is hot, and there it is radiating energy. That radiation travels to Earth. Doesn't matter, there's nothing in between. And in fact, you can find the power due to radiation transfer using this equation. Now, in this equation, there we go. E is known as the emissivity. It is simply a constant from 0 to 1 for a topic to say how well it emits. A is the surface area of the object. Sigma is called the Stefan Boltzmann constant. We already talked about the Boltzmann constant. This is the different one. This is the Stefan Boltzmann constant. And there's its value. And T is the temperature of the object. Now, it's kind of interesting because right now, I exist, I'm radiating energy. This air right here that I'm sitting in, it exists too. It was atoms, so it's radiating energy. My desk is radiating energy. The general idea is, for the most part, well, for everything is always radiating energy, unless it's at 0 Kelvin. But you're also absorbing energy from everything else. Because even though I'm radiating energy, I'm absorbing energy of all the things around me. In general, if an object is hotter than its surroundings, like I say we have an object that's a temperature T surrounded by an area T sub naught. That's my little picture here. If something is hotter than its surroundings, it will radiate more energy than it absorbs, and it will cool down. If something is colder than its surroundings, it'll absorb more energy than it loses, and it will heat up. This is why if it's like 70 degrees out, you feel fine, you're kind of used to radiating some energy. But if it gets hotter than your body temperature, it's really, really uncomfortable. That's because you're absorbing heat faster than you're losing it. And in fact, at all times, all things are radiating energy using that equation, EA sigma T to the fourth. But at all times, you're absorbing energy from everything around you, where it'll be EA sigma T naught to the fourth, where T naught is the energy of your surroundings. And so you have a net power difference of just the two subtracted from each other. And at all times, you are emitting energy and you're absorbing energy, and you have a net gain, depending on which one's happening faster. If you have a radiator in your house, that's what a radiator is. Radiators also have convection because they have hot air touching. What it is, they just get real hot. Because they get real hot, they emit a lot of radiation. They emit a lot of radiation, heats things up. And when I say things like that, it emits radiation, most people freak out and be like, oh no, radiation, we're going to get cancer because, you know, radiation. Radiation's more complicated than that. The whole, like, this is radioactive radiation, that's just a type of radiation. But all things emit electromagnetic radiation. Electromagnetic radiation is perfectly fine. This, though, this electromagnetic radiation, this is why if you go out on a hot day and step on the blacktop, it's really goddamn hot. Things that are colored black are very good at absorbing things. The emissivity value is high, and so they heat up more. Something white doesn't absorb heat as well. It reflects the light, has a low value emissivity. It won't heat up as much. Any questions? Okay, so you might have noticed I've given two different equations for power in this chapter. The top one is conduction. The bottom one is radiation. That's all it is. They both are power by heat transfer, just for two different mechanisms for heat transfer. Okay. Other things about radiation. As I said, all things radiate, but we can only see things that radiate energy with a certain amount of energy. That we have a range that we can see. That if things get really hot, we can see them radiating. You take a piece of metal and you put it in a fire until it's red hot. What it is you are seeing the radiation. You got it bright enough. However, at all other temperatures, there will be radiated energy. Thermographs are pictures taken where you can map heat. And what it is we have been able to make devices like heat vision, go all Predator style on this. We can make devices that can look at radiation in the infrared and shift it to the visible. It is sometimes used, people use this sometimes to look at houses and see where heat is leaking through, where they need more insulation. It's also used in medical fields. It can be helped to find cancerous cells. 310 Kelvin is about body temperature. 312 Kelvin is about the temperature of cancerous cells are at. If we look at the heat radiating from a body, we can see where shit's going bad. And I don't know why there's a picture of a dog here, but I just like this picture and I keep using it. Loses a lot of heat around its eyes, apparently. Now, let's say you got something and you want to minimize heat loss. You want to get something cold, keep it cold, and not have anything else be cold. Never get hotter. Well, eventually will, but minimize it. The device best created to keep heat transfer is something that's going to have to take care of all three of these: conduction, convection, radiation. That if you're worried about heat loss, you can't worry about just one of the conduction, convection, radiation. You got to deal with all three. And one of the best devices created to take care of all three is a thermos. Fuck. I grabbed the opening as I flipped that. Normally I can flip it, but I grabbed at this spot and just poured water all over my lap. And now I'm cold because conduction. Well, at least it wasn't over my keyboard. Cool. Okay, let's continue. Oh. Conduction. A good thermos. This thing, if I put ice in here, it'll keep ice all day long. Like, why? How did I do that so bad? Okay, it'll keep ice in all day long. It'll stay cold. The water in here is actually taken from my fridge and is still cold from this morning. The reason why is because it's taking care of all three of these: conduction, convection, and radiation. What it is first off, I said before it had two walls. It's kind of like that picture there. That what it is, so I'm going to step off the side again, clean some water off myself, is that it has an inner wall and an outer wall, and it's filled with a vacuum in between. What that means is that there'll be no loss by conduction, or minimal loss by conduction, just through the top. See, cleaning up water as I teach. See, if you have nothing for the air molecules to hit, the air molecules don't hit anything. It's as simple as that. I mean, yes, it can go at like the top, but it's going to be minimal compared to the whole shape. What you also do is you put a top on it. If you put a top on it, there's no air blowing over. Open this up. Now air is blowing on it. There's convection. You put a top on it, there's no airflow, no convection. There you go. Problem solved. But you might notice most thermoses are silverish in color. They're shiny. Radiation is electromagnetic radiation. It's light. You don't want something to lose energy to light? Use a mirror. They're always made silver because the electromagnetic radiation will bounce off instead of penetrating. That light bounces off shiny surfaces. And that's the same as electromagnetic radiation bounces off shiny surfaces. That the inside of this thing is shiny to have the light bounce off. It's also usually glass inside. Glass is just because it has a low value of Kappa. Although this one is metal on metal. This one's not glass. It's not as fancy. But you silver the inside. You make it shiny to reduce the heat loss. Okay? Any questions? I can't believe I just poured water all over myself. Okay. The end. That's it. That's all we got. That's the end of the chapter. And by the end of the chapter, I mean the end of the class. By the end of the class, I mean except for the final, a lab and a homework and another homework and example problems on Friday. But that's the end of the PowerPoints. So there we go. Hope you at least somewhat enjoyed the class. Being online sucks, and I fully acknowledge it. I already did a review for the final. I will, Friday's class, we'll go through and I'll do practice problems from this chapter. Don't forget your last two homework assignments. There we go. Have a good day.
Thank you. Have a blessed day.